class, to figure out the minimum weight spanning tree. So here's a graph. So like the number connecting an edge tells you the weight of that edge. And the problem here is finding a tree that's inside this graph that includes all the vertices of the graph and that has minimal weight. So that's the problem. And so let's use this as an example. And let's follow Kruskal's algorithm. So the plan here is you choose edges with minimal weight, avoiding cycles. That's kind of the philosophy of it. Okay? So if, I mean, there's a lot of edges there. Well, what's the smallest weight you see? I think the smallest weight is 20. And let's try to recreate this guy. Let it be range. So I guess it's an inch. Am I missing any? I guess I'm missing GD. complicated graph. So we have the edges. Let's see. So which ones are connected to A? We have AI weight 43. We have AL weight 56. We have AG weight 25. So those are all the ones that have A. Now let's look at IC 79, IF 29. We have CB 39, CH 79, CK 23. Alright, so we've handled AIC. Let's do H now. HJ 92, HK 84, HE 88. Alright. So let's do EK is 59, EM is 66, no, 49. KM is 66, DM is 68, and DK is 58, DJ is 56, DG 71, DL 55. We have LJ is 88. So I think that covers all the outer vertices. And then we have FB 38, FJ 30, FG 26. What about B? So B is connected to K and to J. So 87, 34. Alright, what are we missing? I guess KJ, 83. And we have GJ 96. I think we got all the edges there. So let me know if I'm missing any. So am I missing any? How many? pages did we have there? Let's see. So I have 27 there. Alright, let's suppose it's correct. So then what the algorithm does is you order these from shortest to longest. So you sort it. So shortest is 23. And then I think the next shortest is 25. This is sorted. And then what's the next shortest? 26? Then the next shortest is 29, I think. Okay, what's next?
34.
30, then 34. Alright, what's next? Is it 39? 38. 38. And then 39. Okay, what's next? I see a 43. Okay, so it's 43. Alright, what's next? 48?
No.
Oh, maybe that's what I missed. I thought there was a 48. Okay. Alright, 49 is next. Where is it?
Ian.
Alright, what's next? Then we have a couple of 56s. Okay, what's next? 58, then 59? Alright, what do we have? Yeah, 66. And 68, I think. 71. Okay, IC and CH. radiates, so HE LJ, and then the 92, and then the 96, right?
Is this like stable?
What?
So if they're duplets, do you just go in order?
What?
If they're duplets, you just go in order of.
Yeah, you can pick whatever order you want actually. All right, so again, the algorithm is you choose edges with minimal weight, avoiding cycles. So we grab CK, and then AG, so we don't have a cycle, then FG, so we use and then IF, and FJ, and BJ, and then the next one is FB, but that would give me a cycle, so I don't use that one. And then BC does not give me a cycle, so I can draw it. And then we have AI. AI would give us a cycle, so we don't draw that one. And then EM is, where is EM?
It's
Right.
49.
49.
49. Oh, this one. Okay. DL also looks legal. AL, there's no cycle. And DJ, DJ would form a cycle, right? And DK, I think that also forms a cycle out here. So DK, EK, ah, it forms a,
It doesn't.
okay. So far we've used most of the vertices, right? The only one we haven't used is H, I think. Well, probably it's gonna be HM. Oh, but there's no HM. Alright, whatever. Let's see, so KM, does that form a cycle? It forms a cycle. DM, DM also forms a cycle, right?
Mhm.
Yeah.
DG, cycle. IC, a cycle. Yeah, I guess it forms a cycle. IFJBC. Like this big triangle. Okay, CH.
It's good.
There we go. I think that works. And then we stop because every vertex has been used. So that those pink edges are a tree because there's no cycles, and it's spanning because it covers all the vertices. And then we haven't showed his minimal weight, but you can kind of see why it should work. I mean, it still needs to be proved, but the idea is, well, we're picking the smallest weights to begin with, so it should kind of work. But we'll prove it later that it works. But this is Kruskal's algorithm. It's kind of surprising that it works. I mean, there's just one philosophy: avoid cycles, and you just keep picking the minimum weight. So it's a greedy algorithm. You keep picking the minimum weight, and then even though there were like the edges appeared all over the place, right? Like you have CK here, and then the next one was AG. Like they're not connected at all. So you're starting with this thing that's like the edges all over the place, and at the end you get a tree. So everything is connected. If you want a path from L to H, then you can go L, A, G, F, J, B, C, H. So if you pick any two vertices, there's a way from getting from one vertex to the other. And yeah. So if you kind of want to see it in pseudocode, the idea is that you start, so like kind of the steps of the algorithm are, so steps. So first you sort the edges by weight. You start with the empty set. You also have your initial edges, which I guess I'll call T, they're both empty. And you do something like while the size of S is less than N, then you're gonna choose how would you describe the edge of less weight? Thinnest edge? Smallest? Smallest?
Lightest?
Lightest, there we go. Thank you. Choose lightest edge that doesn't form a cycle. Right, so then once you chose that, let's say the edge is like, so if the edge is x to y, then you add, so S will be the same as the union of x with x and y, and T will be the union of T with the vertex x comma y. Right, so in theory, sometimes when you add an edge, the size of your tree grows up by 2, right? So like when we went CK then AJ, we started with 0 vertices. After CK we have 2. After AJ we have 4. And after FG now we have 5. So each time you're adding an edge, either you added 1 vertex or 2, depending on whether X and Y. So one of these two will not be an S, but maybe both of them are not an S. And this edge is definitely not in the tree. So you just keep building this, and then the output at the end is a tree, right? So you're checking, this N is the number of vertices. In the graph. So this is Kruskal's algorithm. And I'm going to use the same drawing. And I'll also keep this edges here, but I'll delete those. Although, well, I won't delete them because it's still useful to have the weight sorted just to make searching easier. But in Prim's algorithm, you don't need to sort. Alright, so where can I write? I guess right here. So Prim's algorithm is another type of 3D algorithm, but the philosophy is a little different. So with Kruskal, is like you just keep throwing edges, making sure that there's no cycles. With Prim's algorithm is kind of you're building the tree. So this is a build the tree algorithm. Again, just before I go into it, over here, like you're just putting edges, and at the end you get a tree, right? There were several moments on which we didn't have a tree. With Prim's algorithm, every step of the way you have a tree. So you start with a root. So which vertex here do you want it to be the root?
J.
Let's pick J as the root. This is going to be my root. So now I look at all the edges connecting to J. So I have JF, JB, JK, JD, and JG, right? So those are there's one, two, there's 6 of them, or JL also. 1, 2, 3, 4, 5, 6. There's 7 of them. So among those 7 edges, I pick the one of smallest weight. So that's 30. So I draw that. All right? So now I look at every edge connected to F or J. All right? And I pick the one of smallest weight. So among everything connected to J and F, the smallest weight would be this one, I think.
What about
FG.
F2?
Thank you. All right. Just testing whether you're paying attention. Good. So FG is the one. I guess so. Yeah. All right. So we have sorted things. So you pick a root, then you grab lightest edge connected to J, which is JF. Then you pick the lightest edge connected to either F or G or J, which is GF. That path so far. Now I pick everything connected to F, G, or J, and I pick the one of smallest weight. So that looks like it's going to be the 25. All right, so then I pick the thing that has smallest weight that's connected to either A, G, F, or J. It seems hard to be 29. So far it's creating like the same tree. So now we look at all the edges connected to A, G, F, J, or I. And you pick the smallest weight. And that is, I think, this one, right? Fi and then Bj. So I guess we can keep track of which things we have selected. I'm wishing I hadn't sorted. Where's the 26? Here. Alright, 25, 29, 34. Alright, so then, like, say we're at this stage, we're looking at everything connected to either A, G, F, I, J, B. Anything that's connected to that, and you grab the one with smallest weight.
39.
Is
It's
it
gonna
39?
form- It's gonna form a cycle, 39.
Oh, I see. Yeah, well, yeah, you also do it avoiding the cycle. Yeah, so otherwise you form a cycle here. Good point. So you build a tree, avoiding a cycle. Oh yeah, building a tree. So if you have a cycle, it's not a tree, right?
Yeah.
So you pick the lightest. So here the steps are pick a root, and then you're going to do a while loop where you choose a vertex, an edge, a light edge that builds a tree. So the pseudocode is something like you have your initial edge is your root, your tree is empty, and then you do a while loop while the size of S is less than n. Then you find lightest edge of the form xy, where x is in S, y is not in S, and adding xy does not create a cycle. So then S will be S union Y, and T will be T union XY. So you add this edge to the tree, and you add that new vertex to S. So this one is actually well, this one, each step of the way, the size of the tree is growing one vertex at a time. So the other one, Kruskal's algorithm, sometimes you get two new vertices. With Prim's algorithm, you grow one at a time. One advantage of Prim's algorithm is that you don't have to sort the things overall, but the disadvantage is that on each step of the way you're kind of sorting what's connected to them. So you still have to do the sorting and such. And like you can still think of it as, I mean, once we have all but one, you will see what's connected to everything but the last one. So you still have to sort something. So you sort like in every step, which is not optimal. And the other thing is like each time you have to figure out what are the things connected to it, right? So at first it's easy. There's 7 things connected to J. But once you have J and F, now you have a bunch of things connected to J and a bunch of things connected to F. And each time you add one more vertex, you're just adding things that are connected. Now, once you pass the middle of it, then it's almost like what things are not connected to it. Because you're only looking at things connected to this that are not already in the set, right? So, if you well, actually, you don't actually need to check this, because if y is not an S and x is an S, then you can't have a cycle. Right? So the advantage of Prim's algorithm is that the avoiding cycles is automatic, because you're only checking things where one vertex is in S and the other one is not in S. So you automatically avoid cycles. So with Kruskal's algorithm, the step that's hard to analyze in terms of the running time is the part where it doesn't form a cycle. Like, how do you check if it formed a cycle or not? If you're looking at it, it's easy. But if you're coding it, how do you code for your computer to know that something's not a cycle? So that's not obvious how to do it. And the next lecture is a suggestion how you could do it that runs relatively fast. So the step that's time consuming is that part. The sorting, as we know, is just n log n, so that's fast. And this while loop will not, you won't do that many steps because s keeps growing by either 1 or 2. So if avoiding cycles is fast, then this runs in big O of n, and that one was big O of n log n. So obviously you're still bounded by n log n. So once you know how to avoid cycles, that's a tricky part. With Prim's algorithm, the annoying part is this can be time consuming. You have, well, isn't that time consuming? I guess. I mean, it still seems like an easy bound is number of vertices times number of edges. Well, actually, this is kind of, so it's definitely big O of n squared. So that's not so bad. But yeah, coding it, or even coding it is not that bad, because you can just, you have your set S. So you look, you put that in your left coordinate, you see how many edges have a coordinate in S and a coordinate not in S. You list them and you grab the minimum of those. Boom, you added it. So it's pretty straightforward to code it. And what happened to, so if you just keep doing it, once you have these guys, then you get that, and you get this. And then you get this, and you get this, and you get this, and you get this, and you get that. And you get the same tree. I think that's what you have. Let's see. So when you have B, this is the smallest one, then clearly 23 is the smallest one. Things connected to KC, so the candidates, I guess, are 56 or 56. All right, so you could have, instead of chosen this, you could have chosen that one. So you have a choice. 56 and 56 tie. So instead of this one, you could have chosen that. That happens when we have K, C, B, blah, blah. And once you add D to it, then this is the smallest one. That's force. And once you have D and L, then the smallest one is that one. And once you have all of those, the smallest one is this. So you build either the same tree or changing this or that. And they both have the same sum, so they're both minimal in that setting. So next class we'll show that these algorithms do give you a minimal spanning tree. And then I'll talk about, well, how do you code this avoiding cycle business? Okay. So if you're looking at homework 7, in homework 7 there's a problem where I give you a graph
Is that 270 home?
simpler than this one. And you have to find the tree
They
using
commented.
Kruskal and find the tree using Frick. Yeah.
So you chose the root 2 here. You can just pick a random one.
You
There's
can
no,
pick
like,
any random one. So you have complete freedom in which one you pick. So if I'll share this notes with you. In the notes they pick A as a root. Alright.